Welcome to our series on RAG, Retrieval Augmented Generation. We're experimenting with new ways to teach AI. First one is using popular storylines to make complex concepts stick. We really want to know, is this working for you? Whether it's too simple, too dense, or just right, your feedback helps us improve. Leave a comment with your thoughts, what works and what doesn't, or perhaps suggestions for future topics. If you find this helpful, don't forget to like and subscribe.
Welcome to the operational overview of Operation Vector Strike. What you're seeing here is a real-time dashboard illustrating the process of target acquisition in high-dimensional search spaces. This operation demands speed and scale. Notice the metrics in the top left. Our scan rate is a blazing 12.4 terabytes per second, and we are achieving nearly instantaneous performance with latency below 0.01 milliseconds, maintaining coverage globally. Our search parameters are highly advanced, employing multimodal analysis and adaptive pattern matching, meaning the system learns and evolves as it processes data. The central element of the display is our search vector, currently focused on a target area centered near South America. In the bottom left, we have achieved preliminary detection. Target signature detected, 1A7X. The confidence level is currently rated at 94.7%, classifying this as a high threat level event. The primary challenge of Operation Vector Strike is moving beyond simple keyword matching to find semantically relevant targets within billions of potential data points in milliseconds. This dashboard encapsulates the culmination of advanced retrieval augmented generation techniques designed to prioritize actionable intelligence while maintaining optimal system integrity across the entire operational theater. Our mission objective defines the core difficulty of this entire exercise. We must find a single signal in what we refer to as a continent of noise. Imagine trying to sort through a digital library the size of a continent, containing over 1 billion unsorted books or documents. In traditional data search, a brute force search, known mathematically as exact K nearest neighbors, would be required. While this method is mathematically perfect, guaranteeing the discovery of the target because it scans every single point, it is operationally unviable. It simply takes too long to be useful in a time-sensitive situation. The key realization is that our mission requires actionable intelligence now, not perfect intelligence tomorrow. Therefore, we must make a strategic compromise. We employ Approximate Nearest Neighbors, or ANN. By accepting a fractional loss in accuracy, for example only 1%, we gain an exponential advantage in speed, typically around 1,000 times faster than brute force. As the visualization shows, instead of scanning every data point, the ANN search is mission-capable because it jumps directly to the relevant region where the approximate neighbors cluster. This strategic compromise is the foundation upon which modern, high-speed vector search architectures are built. To ensure maximum efficiency and precision, we deploy two specialized teams, each utilizing a distinct methodology that, when combined, forms a robust hybrid search system. First, we have Team Recon, responsible for dense retrieval, primarily using vector search. Think of Team Recon as the intelligence operatives. They work based on context, patterns, and semantic feel. Their objective is to find targets that fit the profile of the threat, even if the exact keywords are never explicitly used. Their core expertise lies in uncovering deep semantic relationships and hidden meanings within the data. Second, we deploy Team Strike, focused on sparse retrieval, using the traditional BM25 or keyword search methods. Team Strike operates like the direct action unit. They rely on explicit orders and exact matches. They find targets that match specific call signs, names, or codes mentioned precisely in the intel briefing. Their expertise is high-precision targeting based solely on explicit information. By running both dense and sparse retrieval in parallel, we gain comprehensive coverage. Recon finds the things conceptually related, and Strike ensures we do not miss any known identifiers. This dual methodology is crucial for generating a complete and reliable list of potential targets. To navigate a billion-point data landscape at speed, we cannot afford to wander aimlessly. We need a map. This structured map is what we call the index. The index is the fundamental technological innovation that makes high-speed vector search possible. Our goal is to transform the search from a slow, linear scan, which is mathematically represented as O of n, where n is the number of data points, into a fast, logarithmic jump, represented as O of log n essentially. The index allows us to ignore 99.9% of the environment and move directly to the relevant sector. We transform the vast, unstructured data landscape on the left into a highly structured and navigable space on the right. Currently, there are two dominant architectures used for building these indexes. The first is the clustering approach, such as IVF, which divides the map into discrete, manageable zones. The second, and the architecture we favor for its advanced capabilities in high-dimensional space, is the graph approach, known as HNSW. HNSW builds a multi-layered, sophisticated transit system, analogous to a transportation network, to ensure the fastest possible pathfinding to the target vectors. Our primary navigation system for traversing the vector space is the HNSW Transit System, standing for Hierarchical Navigable Small World. This architecture operates much like a sophisticated multi-layered transit grid, leveraging the 6 degrees of separation theory to connect distant points quickly. It allows our search operatives to traverse the entire massive operational area with logarithmic speed. We break the HNSW system down into 3 key conceptual layers, each serving a specific function in navigation. At the top is the top layer, which we analogize as the bullet train. This is a very sparse network of connections linking the major hubs, used for traversing vast distances almost instantly during the initial search phase. Below this are the middle layers, the commuter rail. These layers provide denser connections necessary for smoothly navigating between regional sectors and local zones. Finally, we reach the bottom layer, the neighborhood walk. This is the densest layer where every single data point is connected to its immediate neighbors. This layer is reserved for the final, localized, high-precision search once the system has successfully routed the query to the correct neighborhood. The HNSW search path is a rapid descent, moving swiftly from a high-level, satellite view down to the street corner level in logarithmic time. Following the broad sweep, we encounter a crucial stage known as intel fusion. The scenario is this: Team Recon, our dense retrieval unit, and Team Strike, our sparse retrieval unit, return with their own separate ranked lists of potential targets. These lists often conflict slightly. One team may rank a high-priority target, such as Target Bravo, at number 3, while the other team might have it lower, at number 5. Our task is to create one definitive, superior priority list from these disparate inputs. The protocol we use for this is reciprocal rank fusion, or RRF. RRF is essential because it is a strict, non-learning algorithm specifically designed for combining ranked lists mathematically. It operates by assigning weighted scores based on rank, heavily prioritizing targets that appear consistently high across both lists. It is specifically designed to suppress targets that only scored highly on one list but were missed by the other. This fusion process creates a unified result that is statistically superior to relying on either individual input alone. As demonstrated, RRF successfully elevates Target Bravo to the number 1 spot on the unified priority list, providing us with the most confident signal for final action. A foundational principle in search operations is garbage in, garbage out. A high-tech, lightning-fast search system is rendered useless if the initial query, the command directive, is flawed, ambiguous, or incomplete. Therefore, the most critical phase of our entire operation is Phase 0. Mission success begins before deployment. This phase is dedicated entirely to refining the objective before we even initiate the broad sweep search. Our objective in Phase 0 is handled by the Query Transformation Layer, which utilizes a fast, tactical large language model, or LLM, to function as an expert analyst. This LLM cleans and clarifies the incoming intel, which is often raw and highly ambiguous, producing a search directive that is clean and actionable. We rely on 3 key tactics within Phase 0 to achieve this refinement. They include hypothetical target profiling, known as HIDA, which helps us bypass vector space limitations, deconflicting ambiguous comms via query rewriting to manage conversational history, and parsing field intel using the self-query retriever to handle embedded metadata constraints. This essential preparatory phase maximizes the precision of our search vector before it even touches the main database. The first essential tactic within Phase 0 is generating a hypothetical target profile, or HIDA. This technique relies on a crucial insight regarding high-dimensional vector space. A question, such as how to bake a cake, and its factual answer, a long document detailing the steps, can often be surprisingly distant in vector space. However, we have observed that two answers to similar questions are almost always very close together. HIDA exploits this disparity. We use the tactical LLM to generate a profile. Instead of embedding the original, distant question, we instruct the LLM to generate a hypothetical, often hallucinated, answer, such as a description of the necessary ingredients and process. We then embed this hypothetical answer into a vector. When we deploy the search, we look for real documents in the database that match this highly effective profile. The HIDA result is powerful. It bridges the semantic gap between the question space and the more reliable answer space, thereby creating a significantly more effective and precise query vector that improves retrieval accuracy, especially for conceptual or abstract queries. Our second tactic in Phase 0 addresses the challenge of deconflicting ambiguous communications, which frequently arise in multi-turn operational interactions. The core challenge is that field operatives naturally rely on context built up over the course of a conversation. The failure mode occurs when we send a context-dependent query, such as, "How old is he?" directly to the retrieval database. Because the database lacks the conversational history that identified he as Tim Cook, the query is mission failure. It is impossible to resolve. The solution lies in query rewriting, performed immediately by the analyst layer. This sophisticated layer intercepts the ambiguous query and uses the preceding conversation history from the intel stream to rewrite the ambiguous instruction into a precise, standalone directive. As you see, the incomplete "How old is he?" is transformed into the actionable, self-contained directive. "How old is Tim Cook?" This ensures that every single query vector that enters the main broad sweep system is entirely unambiguous, maximizing retrieval success by preventing context loss. The third tactic for Phase 0 focuses on translating complex field intel into structured queries, a process critical for handling filters. The challenge is that natural language requests often contain both a topic and crucial constraints. For example, an operative might ask, "Show me email security protocols from last year." A traditional, simple vector search would effectively find documents about email security protocols, but would completely ignore the vital from last year filter. This leads to information overload and mission delays. The solution is the self-query retriever. Here, we utilize the LLM not for generating answers, but strictly as a parser. The LLM translator understands the operator's intent and, crucially, understands the database's metadata schema, which dictates how dates or years are stored. It takes the unstructured natural language input and translates it into a structured JSON output. This structured output explicitly separates the vector query from the metadata filter. The system then executes a combined, filtered vector search, ensuring it retrieves only documents relevant to the topic and satisfying the required constraint, such as the year 2024. After successfully executing the broad sweep and intel fusion via RRF, we enter the final verification stage, overseen by the Overwatch analyst. The situation is that the fused list provides our top 5 to 10 most likely targets. However, because the initial search methods were optimized for speed using Approximate Nearest Neighbors, they can sometimes suffer from the lost in the middle problem, where the single best target is ranked lower than a few superficial matches. The protocol requires that before any final action is taken, these top candidates are passed to a senior specialist for meticulous, resource-intensive verification. We call this necessary step post-retrieval ray ranking. The primary goal is to confirm the number one target with the highest confidence possible, and just as importantly, to eliminate any red herrings, false positives, or candidates that superficially match the vector that may have surfaced during the initial high-speed sweep. The verification process acts as a final filter, ensuring maximum precision before actionable intelligence is delivered. The asset employed by the Overwatch analyst for this final verification is the cross-encoder model. This model represents the ultimate in precision. Its methodology is fundamentally different from the fast retrieval models used earlier. Those models use a dual encoder approach, creating separate vector embeddings for the query and the documents before comparing them. The cross-encoder, however, performs a deep semantic analysis by examining the query and the candidate document together in a single attention mechanism. This allows it to determine the true relevance score with incredible accuracy. However, this power comes with a significant trade-off. The power is its extremely high accuracy. It performs a deep semantic verification to confirm genuine relevance. The cost, however, is that it is computationally expensive and slow. Therefore, we utilize it surgically. It is only deployed on the handful of top 5 or 10 candidates returned by the initial high-speed search. This strategic use ensures we pay the computational cost for high confidence only when absolutely necessary, achieving a relevance score that approaches 0.98 for high confidence matches. This summarizes our mission debrief, detailing the complete architectural loadout that drives Operation Vector Strike. Our process is a linear, 4-stage pipeline. Phase 0 refined the initial query into a precise directive. The broad sweep deployed dual teams, recon and strike, using the HNSW navigation system. Intel Fusion merged the results with RRF for a unified priority list. Finally, final verification utilized the cross-encoder analyst to confirm the primary target with maximum precision. A critical infrastructure decision remains the database. We have 2 core options. The first is a dedicated vector DBS, such as Pinecone or Weaviate. This is a specialized, high-performance platform ideal for massive-scale operations, analogous to a dedicated command center. The second is integrated vector search, like PG Vector. This adds vector search capabilities to an existing standard database, analogous to embedding a signals expert into an existing field unit. Our operational verdict is to choose dedicated databases for massive, purpose-built scale operations, but to start with integrated solutions for existing applications that need to quickly upgrade their vector search capabilities. Signal confirmed. Mission success. The conclusion of Operation Vector Strike underscores a vital core takeaway for modern intelligence and data retrieval operations. Modern target acquisition is not a single action, but a sophisticated, multi-layered pipeline designed for both incredible speed and uncompromising precision. Our architecture deliberately combines high-speed, broad-spectrum retrieval with layers of intelligent refinement deployed both before and after the initial vector retrieval. Phase 0 refinement ensures the query is clean. The dual sweep ensures broad coverage. RRF fusion optimizes the list. And cross-encoder ray ranking ensures the final target is confirmed with unparalleled confidence. This disciplined, staged approach ensures that the output is not just data, but the right, verified information delivered at the critical speed of relevance necessary for mission success.